Good morning. My name is Matthias-Fresacher, and today I'm going to tell you about the congruence lattices of finite twisted Brauer and Temperley-Lieb monoids. As the title suggests, there's going to be two main ingredients for this talk, monoids and congruences. Both of this I'm going to explain as much as possible through the use of pictures and diagrams, keeping the notation to a minimum. That will then allow me to state the results I was able to prove in the last couple of years. Let's get into it, and we're going to start with some motivation from the field of statistical thermodynamics. In this area, the atomic interactions between atoms are modeled by matrices. Specifically, these matrices are elements of an algebra, the twisted semigroup algebra, where the semigroup is a Brauer monoid. This whole construction is typically called a Brauer algebra. So we can see if we get a better understanding of the Brauer monoid, in this example, we get a better understanding of statistical thermodynamics. This is not the only example, there's others in the fields such as biology, representation theory, invariant theory, as well as knot theory, just to name a few. What exactly is a monoid? Well, it's a set together with a binary operation, usually denoted by multiplication. And that operation has to be associative. By that we mean if you multiply three things together, the order in which we do that doesn't matter. If that's all we have, then we have a semigroup. If we include the addition of an identity element, then we have our monoid. We're going to be interested in two specific monoids. The zero-twisted Brauer monoid. This has as its elements the Brauer diagrams, which are usually pictorially depicted by two rows of vertices. And what makes two different diagrams different are their edges. So the Brauer diagrams have the condition that every vertex must be connected to exactly one other vertex. A pairing up of vertices, if you will. We're also going to be interested in the zero-twisted Temperley-Lieb monoid. This is sometimes referred to as the Jones monoid. For those of you with keen eyes, yes, this is the same Jones as the author of the motivating paper. Temperley-Lieb is actually a sub-monoid of the Brauer monoid, so quite often I'm going to be talking about the Brauer monoid, I implicitly imply Temperley-Lieb as well. Being a sub-monoid, its diagrams need to have an extra condition, and that condition is that edges are not allowed to cross like they do up here. The graph must be planar within this box. You're not allowed to have edges going around the outside. We can talk about the degree of an entire monoid, and this simply counts the number of vertices in our row. So both of these belong to a monoid of degree 5. We can talk about the rank of a specific diagram, and this simply counts the number of transversal edges. By transversal, we mean linking both the top and the bottom rows. So we have 1, 2, 3 transversals. This diagram has rank 3. Here we have a rank 1 diagram. It holds that the rank and the degree always share the same parity. We also have a zero, well, we call it a diagram, even though strictly speaking it's just an abstract construct. It doesn't have a pictorial representation. And just to avoid confusion, that zero doesn't have much to do with that zero here. Concatenation, well, that's the multiplication operation of our monoid. For those of you that are visual-based learners, this is an animation of that procedure in action. And for everybody else, I'm going to make use of this intermediary step to explain how we end up at the concatenated diagram. So let's go through the steps for calculating alpha times beta in some detail. First, we position the two diagrams one directly on top of the other, and then we draw these red vertical in-between edges. We then remove the two inner rows of vertices, and we remove any loops that are present. So a loop is any collection of edges that are not connected to the top or the bottom row of vertices. So there's an example of a loop here, and there's a second example just here. And then we tidy up what we have left. So we're going to squish our rows back to normal size, and we're going to draw clean edges where they exist. Except I lied. What we just went through is the non-twisted concatenation. The zero-twisted concatenation is as soon as we encounter a loop, as is the case in this example, then by definition we have the zero diagram. Pictorially, you can probably convince yourself that this is in fact an associative operation. It does have an identity diagram, specifically just all vertical edges, but it's not necessarily going to be a commutative operation. For those of you that are familiar with it, this does correspond to a Brauer, respectively Temperley-Lieb algebra with a twisting coefficient equaling to 0. Now let's move on to the congruences. What are they? Well, they're an equivalence relation, usually denoted by sigma, on our set of diagrams. But it must be compatible with concatenation. And by that we mean if I take two diagrams, an alpha and a beta, if I multiply on the right, I still want that pair to be congruent. And I want a similar property to hold for on the left. Some easy examples include the universal congruence, where everything is congruent to everything else, or the trivial congruence, where everything is only congruent to itself. In between these two extremes, we're going to have a congruence lattice. So you can picture this as the trivial congruence sitting at the bottom, universal congruence sitting at the top, and all sorts of different congruences sitting in between these two extremes. We can think of this lattice as a partially ordered set via subset inclusion. So for example, sigma 10 here is a strict subset of sigma 11. Or we can think of this as a lattice with two operations, the join and the intersect operation. So for example, if we take the join of sigma 4 and sigma 5, that gives us the bigger congruence sigma 6. Or alternatively, if we take their intersection, in this case we would get sigma 3, and that's a smaller congruence. If I were to take an arbitrary monoid and look at its congruence lattice, chances are it'd be horrendously complicated, big, messy, and just not of any use at all, really. But it's a remarkable fact that for the diagram monoids, the congruence lattices are very simple and can be as simple as just a chain. We will need the notion of a principal congruence. This is where we take a pair alpha and beta and look at what's the smallest congruence that contains that pair. Why do we care about congruences? Simple, because they govern quotients in exactly the same way that ideals are really important for groups, for rings rather, and normal subgroups are important for groups. And if we go back to the motivating example, it's usually not the entire Brauer monoid that appears, it's actually a quotient of it. So for us to be able to, in that example, gain a better understanding of statistical thermodynamics, we need to understand the quotients of the Brauer monoid, and to understand the quotients, we need to understand the congruences. Before we continue, we're going to take a quick detour into some semigroup theory tools, specifically Green's relations. These are some equivalence relations on our set of diagrams. First, we have the R relation. Two diagrams are related if their top row is the same. And by that we mean if a vertex is part of a transversal edge, in the other diagram it is also part of a transversal edge. And similarly for non-transversals, they also match up across both diagrams. But for those non-transversals, it's really important to note that the actual edge must also be the same across both diagrams, otherwise they are not R-related. Analogously, we have the L relation, and this is where the bottom row of our two diagrams has to be the same. We can take the intersection of these two, that gives us the H relation, and logically that means both the top and the bottom row of the two diagrams has to be the same. It holds that the H classes are in bijection with the symmetric group of that rank. And we can see that in this example here, we have rank 2 diagrams and we have the two elements of the symmetric 2 group appearing. That bijection is going to be important, so just keep it in mind for later on. And also keep in mind that for Temperley-Lieb, the H relation is trivial. And we can see that fairly easily. You think of your favorite symmetric group, think of all of the elements that don't contain any crossings in them. There's not many of them. There's only one, the identity element, pretty trivial. Instead of the intersection, we can take the join. That gives us the D relation. And the D classes for this monoid are all of the diagrams with a given rank. The ideals, well, those are all the diagrams with a given rank or less. And the final ingredient we're going to need is the hat map. This is defined for even degree only, and essentially what it does is it takes a pair of transversal edges, and it annihilates them in the obvious way that you would expect. That now allows me to state the congruences we are going to need, and I'm going to explain these to you using an egg box diagram, and this is for the Brauer monoid of degree 6. We can think of this egg box diagram as being full of little dots, where each dot represents an element or diagram in our monoid. So at the bottom here we would have the 0 diagram, then here we have the D0 class, so all the diagrams of rank 0, then we have rank 2, rank 4, and at the top rank 6, but that's the entire symmetric 6 group. If two dots, so two diagrams are within the same row, then they are R-related. Analogously, if they're within the same column, then they're L-related. Hence, if they're actually within the same box, then we know they are H-related. So if we say zoom into this top corner here of D2, everything in here has got rank 2, check. If we're within a H class, we need to have both the top and the bottom rows be the same, check. If we're moving within a row, we need to be R-related, so all top rows of these 4 diagrams are the same, check. And if we were to move down a column, we need to be L-related, bottom rows are the same, check. And obviously this repeats across the whole egg box diagram. To begin with, we're going to go through the Riesz congruences, and this is where we take the P ideal and we just collapse it to a single representative. So pictorially, if we say looking at the example of the Riesz 2 congruence, everything of rank 2 or less, that's the second ideal, that's in red here, that's just going to get collapsed to a single representative. And to help you understand these congruences, I'm always going to have a pair of diagrams here that is related by that congruence, and it's always going to be the largest possible pair of diagrams. Next, we have some group-based congruences, and this is where we take the Riesz congruence of the rank underneath as a starting point, and in the rank we're interested in, if we are H-related, recall that gives us a bijection into the symmetric group. If we then also have a group action, which I'm not going to explain or define, then we're also congruent. So pictorially, if we say looking at the alternating 4 group, we have R2, everything in the second ideal being collapsed. And then within a H class in D4, well, the alternating group that's got odd and even elements, we're going to get 2 equivalence classes within the H class. And this gets repeated across each H class in D4. But it's important to note that the equivalence classes are different across the H classes. A different example would be the symmetric 4 group, where again we collapse the second ideal. And this time, the symmetric 4 group action is much more encompassing. In fact, anything that's H-related is going to satisfy the group action. So our H classes are going to get collapsed in their entirety in D4. Next, we have 3 lambda congruences, starting with lambda up. And this is where we take RS2 as a starting point, and we have the extra option if we're R-related and have the same hat, then we're also congruent. So recall RS2, we collapse the 0th ideal and collapse H classes in D2. And then if we are R-related, so within the same row, if our hats are the same, we're also congruent. So potentially, some of these H classes are going to get identified across a row. And this gets repeated for each row with different equivalence classes. Analogously, we have lambda down, and this is where we swap out the R relation for the L relation. So pictorially, that means potentially our H classes now get identified across a column compared to previously a row. And then the final lambda is just plain lambda. This is where we drop the R or the L condition altogether, just their hats need to be the same. And this is actually the join of lambda up and lambda down. Pictorially, this means potentially our H classes get identified across a row or column, just as long as their hat is the same. And our final set of congruences are the mu congruences, starting with mu S2, where we take trivial congruence as our starting point, and in D2, we need to be H related. So pictorially, that means we're going to collapse our H classes in D2. And the final congruence, mu cline 4, the most complicated one we're going to encounter. This is where we take lambda as a starting point, and in rank 4, if we're H-related and have a cline 4 action, then we're also congruent. So pictorially, recall the lambda congruence, everything in the 0th ideal being collapsed, H classes in D2 being collapsed, and potentially being identified across a row or column as long as their hat is the same. And then in rank 4, within a H class, we're going to have the cline 4 action. That gives us 4 equivalence classes. I've only drawn 2 here because I'm starting to run out of colors, but I think you get the idea. And again, that gets repeated across each of the H classes in D4. That now allows me to state the results I was able to prove in the last couple of years, starting with the Brauer result. So for the Brauer monoid, the congruences that I just went through with you are in fact all of the congruences for this monoid. And the congruence ladders in the odd degree is a simple chain where we find the Riesz congruences interleaved with the group-based congruences, as you would expect if you're familiar with this area. And on the even side, we basically have this same chain, except we have 3 diamonds at the bottom. And this is where we find the lambda and mu congruences. From this result, it's not too much more work to show that the Brauer monoid is also congruence permutable. In terms of a proof, well, the first step is to go through and show that all of the congruences that I claim are congruences are in fact congruences. Having done that, I then need to consider every possible pair of diagrams alpha and beta and look at what's the principal congruence that pair generates. I need to show that is contained in my list of congruences and that the list is closed under joins. If I've done that, I can apply a very helpful lemma by East, Mitchell, Rustruck and Tolpe that says that my list of congruences is in fact the entire list of congruences for this monoid. To give you a bit of a better sense of checking all of the different alpha and beta combinations, this is the decision tree that I used, and in red for each of the leaves is going to be the corresponding congruence. So first I check, do we have different diagrams? Is one the 0 diagram? Do they have different ranks? Are they H related? We look at some low ranks on the even side, mostly to pick up on the diamonds. And over here we need to check if their hats are the same, because if they are, why exactly are they not H related? That will tell us which flavor of the lambda congruence we're going to get. And over here we need to take care of the Klein for action. The Temperley-Lieb result, well, it turns out its lattice is a sublattice of the Brauer result. So recall the Brauer lattice and recall the fact that the H relation is trivial for Temperley-Lieb. So that means the group-based congruence, well, they're not going to exist because they rely on the H relation. And likewise, the mu congruences, they're also not going to exist because they need the H relation. So basically, what are we left with? Well, we're left with the Riesz and lambda congruences. And the lattice on the odd side, well, is still a simple chain, but this time just with Riesz congruences. And on the even side, we almost have a chain with just a single diamond where we find the lambda congruences. Not surprisingly, Temperley-Lieb is also congruence permutable. This research program was started back in 2018 by East, Mitchell, Rustruck and Tolpe, who investigated a number of diagram monoids and established their congruence lattices in the non-twisted setting. This was then followed up in 2022 by East and Rustruck, who established the congruence lattices in the twisted partition monoid. So the next steps for this work would be to go from the 0 twisted setting that I was working in to an arbitrary D twisted setting. But just to give you an idea of the complexity in doing that, this is the congruence lattice when D is equal to just 2. It's a major step up in complexity. And then there is also an infinite twisted version, which again is another step up in complexity. And hand-wavily, we can think of this as D equaling to infinity. That will complete Brauer and Temperley-Lieb, and there's plenty of other diagram monoids where this research program could be applied to. And there are some applications for this work that I'm currently investigating and working on in the area of translational hulls. This work has also resulted in a LaTeX package PM draw that I've developed, and it's available for you to use on CTAN and download. So all of the diagrams in the proof and in the presentation today have been drawn using that package. If you are interested in to learn a little bit more details about this work, I do have a YouTube channel and there is a full-length lecture version talk available on that channel. The links and details are just here. So hopefully by now you have learned some interesting maths with the help of diagrams.